So let's first focus on dipole-dipole and hydrogen bonds. Those two intermolecular forces only occur with polar molecules. Remember from previous chapters, the difference between a polar and a non-polar molecule. Polar molecules, remember, were unsymmetrical. They have polar covalent bonds. Remember all of that stuff. Okay, let's first start with dipole-dipole. The definition of a dipole-dipole, it has to be in polar molecules, and it's basically just an intermolecular force between any polar molecules, It's sort of like this electrostatic attraction between the opposite poles or the opposite charges. So let me throw in a polar molecule. Just ignore the hydrogen bond for now. Let's just focus on dipole-dipole. So let's say I have this molecule over here. Let's say I've got hydrogen. Let's see. If you look at the electronegativity chart, you'll notice that chlorine is more electronegative than hydrogen. So the arrow goes towards the chlorine, or chloride in this case. So this would be partial negative, and this was partial positive. So this is a polar molecule. Now, if I have another HCl over here, same scenario, this is partial negative, this is partial positive. See this partial positive pole and see this partial negative pole? That's where the attraction is. This here, this is the dipole-dipole, dipole-dipole, okay? So it's attraction between polar molecules that have opposite poles. A partial negative is going to be attracted to a partial positive. All polar molecules will do dipole-dipole. Now, hydrogen bonds are a special type of dipole-dipole, and they're a lot stronger. And in a hydrogen bond, the hydrogen has to be bonded to a very highly electronegative element like fluorine, oxygen, or nitrogen. Think of it as fun, okay? So this is not a hydrogen bond here. So even though you have a hydrogen, it's a dipole-dipole. Why isn't it a hydrogen bond? Because it's connected, it's covalently bonded to a chlorine, not an FON. All right, so let's take a look at the definition of hydrogen bond. Hydrogen bond is an extra strong dipole-dipole that occurs when a hydrogen is covalently bonded to a highly electronegative atom like fluorine, oxygen, or nitrogen. And then that hydrogen is attracted to the lone pair of another FON. Hydrogen bonds account for the double helix in DNA. If you've had some biology, adenine, hydrogen bonds with thymine, guanine, hydrogen bonds with cytosine, if you remember that stuff. Hydrogen bonding also accounts for a lot of the folding of proteins. So any of you guys moving on into biochemistry or organic chemistry, you're going to be dealing with hydrogen bonds a lot. But for us now, let's see what a typical hydrogen bond looks like. Let's say I've got a water molecule. So only polar molecules can hydrogen bond, but only the polar molecules that have hydrogens bonded to FON can do the hydrogen bonding, okay? So not only must you have polar molecules, but you must also have a hydrogen bonded to FON. All right, so here we have a hydrogen bonded to oxygen, so great. So let's see some hydrogen bonding occur. If I have another water molecule over here, see, this hydrogen is covalently bonded to this oxygen, and then it can be attracted to the lone pair of this oxygen. This is a hydrogen bond. Let's do another hydrogen bond. Here's another water molecule. Remember, water is bent angular. There you go. Here's another one. Let's do another water molecule. So you can see here, this hydrogen covalently bonded to an oxygen attracted to this lone pair of another oxygen. Here's another water molecule. So every water molecule could, technically speaking, do 4 hydrogen bonds. All right? Will a molecule that looks like this hydrogen bond, it's got 4 hydrogens? Absolutely not. Number one, it's nonpolar, it's very symmetrical. Number two, the hydrogens are not bonded to FON. So the only things that will hydrogen bond are polar molecules that have hydrogens bonded to a fluorine, oxygen, or nitrogen. Okay? And they are the strongest of all the intermolecular forces. Now, the weakest of all the intermolecular forces are the London dispersion forces. The London dispersion forces can occur in polar and nonpolar molecules. So London dispersion forces. These are weak, temporary attractions between molecules, between polar and nonpolar. So they're the only ones that work for the nonpolar. So nonpolar molecules, the only thing they can do is London dispersion forces. Polar molecules, polar molecules can do dipole-dipole, all polar molecules, but polar molecules that have a hydrogen bonded to FON can do hydrogen bonding. But nonpolar and polar, all of them can do London dispersion forces. And these are temporary imbalance in charges. So basically, if you think of it, and the way I look at London forces is you got this really symmetrical molecule here. This is something called butane. Okay, it's very symmetrical, it's very nonpolar. Well, how is it that it would be possibly attracted to another super nonpolar molecule? What are London forces exactly? The way I look at it is that, you know, these two electrons that are in these bonds here, think of them going around the carbon and around the hydrogen. So for a split second, imagine that they're all around the carbons, and so all these hydrogens in that split second, partially negative, partially negative, partially negative, partially negative. Why? Because, sorry, partially positive, partially positive, partially positive. I don't want to confuse you guys, sorry about that. Imagine that the electrons happen to be around all the carbons. So if they're around all the carbons, then the carbons are all partially negative. So all these hydrogens are partially positive. Imagine in that same split second, all the electrons in these four bonds are around the hydrogens this time. So making these hydrogens partially negative, partially negative, partially negative. In that split second, these partially negative hydrogens are attracted to these partially positive hydrogens, and the two molecules have a London force. That's the way I look at it. There's lots of different ways of looking at London forces. Just know that they are temporary, instantaneous. They occur in an instant. The more the molecular weight, the larger the surface area, the higher the molecular weight, the more significant these London forces are. So if you have a big long molecule with lots and lots and lots and lots and lots and lots of carbons, let's say you have a big oil with a whole bunch of carbons, those are going to be attracted to each other more than a smaller surface area. So high surface area, high molecular weight, high London forces. Okay, LF stands for London forces. So London forces are definitely affected by size, all right? The bigger the molecule, the bigger the surface area, the more the molecular weight, the more the London forces. But still, London forces are considered super weak compared to dipole-dipole and hydrogen bonds. All right, in the last video for this section, I'm going to give you guys a few different molecules, and we'll talk about what intermolecular forces those molecules have, and then we'll talk about how this would affect the boiling point of the molecule and the vapor pressure. Because as we're going to find out, the more the intermolecular forces, the more tightly those molecules are attracted to each other, the less likely they're going to escape into the vapor stage. And so if you have a lot of intermolecular forces, as you're going to find out, you end up having a very low vapor pressure and a very high boiling point. And we'll get to that in the next video.